So if we want to have a total solution to control the quality of service, okay, so it's like it's a very interesting analog that, for example, in budgeting your household expense at home. So you need to, if you have a lot of income, then do you need to do a very tight budgeting? No, you don't need to plan financially, because you have your expense is, your income is much higher than your expense. Then you don't need to impose any control, right? It's the same at home, and also the same in a company, right? If you run a company, you're making a lot of money. Do you need to control the expense tightly? No, you don't impose too many control mechanisms to control the expense. But if the income is about the same as expense, then you need to worry about that. You will impose many control mechanisms. You will ask your wife. You will give your wife an allowance of say 10,000 NT dollar per month for credit card expense, right? You will ask your kids to only spend a certain amount of money per month. So you would impose many control mechanisms when the income is not abundant. And the income here is bandwidth. If the bandwidth is not abundant, then you impose many control mechanisms. And what control mechanism we need to impose? First of all, we need to control before they come in, before the traffic come in. Before the traffic come in to this particular link or this particular node, then we need to do a dimension control. We need to control. So this is the job of the control plane. Once the traffic is allowed to come in, then it's the job of the data plane. So in the control plane, you need to do what? You need to for the traffic source to tell the network. The traffic source needs to tell the network how much bandwidth it needs, what kind of delay, latency, performance it needs, how much bandwidth and the delay requirement it needs. So it's the traffic source telling the network. That's by a signaling protocol. So you need a signaling protocol, a protocol for the traffic source to tell the network about its traffic and performance requirement. And then the network needs to do what? QoS routing, meaning you need to route the flow or the connection to a path with enough bandwidth. It needs to route the flows to the path with enough bandwidth. That's the job of QoS routing. It's different from the routing mechanism we mentioned in chapter 4. In chapter 4, we have RIP, OSPF, BGP, right? And they are based on what? Mostly based on what? Either the hop count. The RIP is based on hop count. OSPF is based on link path cost, the cost, or in a sense the delay. And BGP is based on the cost plus the policy. Okay, so they all do this kind of a shortest path or shortest cost, shortest path routing in the internet routers. But now you need to embed a concept called bandwidth. When RIP, OSPF, BGP do routing calculation, they don't have the concept of bandwidth. Okay, I only know the distance, I mean the cost of each link. I don't know how much bandwidth they have. Okay, so now you need to have put the bandwidth as one parameter of the link in order to decide which path to go through. And then each router then needs to do admission control. Can I admit this flow to this link? Okay, considering that the bandwidth it needs. Okay, so then you need admission control at the router. Okay, so once the traffic source specify its traffic and also its performance requirement, and the router routes the flow to the request, routes the request to a certain path that has enough bandwidth. And also during the process, the router has admitted the flow because it has enough bandwidth to admit. Then what's next? Then the data packet begins to flow. It begins to flow the path, flow through the path. And when it flows through the path, the quality of service, the bandwidth allocation or bandwidth requirement needs to be enforced. So I need to do what? First of all, I need to do classification to classify the packet to a particular flow. So if I'm doing a per flow QoS, then when a packet comes, I need to classify this packet into a particular queue. I mean a queue for this flow. So I need to classify the packet into a flow queue, because I have flow queues. If I have 100 flow, I have 100 queues, and I need to classify the incoming packet so that we know where to put, which queue to put the packet, which flow queue the packet belongs to. Okay, that's the packet classification. And the classification is based on what? Based on the header fields in the packet. And if it's a per flow classification, then it's based on 5 tuples, the so-called 5 tuples, which are source IP address, destination IP address, source port number, destination port number, plus protocol ID. So these are 5 tuples. So based on the 5 tuples, you classify the packet into a flow queue. I mean, the flow queue it belongs to. That's a classification. However, if it's a per class classification, then I would just classify perhaps based on a field instead of 5 tuples. We'll see that later. Okay, once I put the packet into the flow queue, I need to do what? Policing. Perhaps this flow says that it needs 3 megabit per second. So I admit, I find a path with enough bandwidth and admit the flow. And then the packet starts to flow. But how do I know it actually is sending 3 megabit per second, but not more? Perhaps it's sending 5 megabit per second. If a flow wants to take advantage, then it will do what? It will declare I will send 3 megabit per second and get admitted. But when I start to flow, I send 5 megabit per second. Then I'm taking advantage, right? Perhaps I'm paying for 3 megabit per second, but I'm using 5 megabit per second. So we need to do policing to make sure that the flow is actually using less than 3 megabit per second. So that's a policing. And there's a mechanism to police that. And once policed, and then it join the flow queue and waiting to be transmitted. But in front of the transmitter, if I'm a transmitter, I'm facing, say, 100 flow queues. I have 100 flow queues, and each of the queue has some packets, and I'm a transmitter. which packet am I going to transmit next is my problem. My problem, the scheduling problem is, how do I decide the next packet to transmit? Or how do I decide which queue to serve next? Okay. Okay, one simple solution is that I take round robin. I serve the first queue a few packets, and then I serve the next queue, and then through the subsequent queues. But can I say I serve all of the packet in the first queue, all of the packet in the second queue, all of the packet in the third queue? Can I do that? No. Then I become priority queuing, right? Priority queuing says that you serve the high priority queue first, and serve everyone in the high priority queue, and then serve the next high priority queue. Okay, then if you are doing this, then you cannot allocate bandwidth. It says that this queue is 3 megabit per second. This queue is 2 mega. This queue is 5 megabit per second. So I need to make sure that each queue gets the allocated bandwidth. Okay, so I can run a priority queue, but I can. How do I run this queue? How do I schedule? There are two classes of algorithm that we will see next. We'll see later. Okay, so after seeing that, you see we need control plan to decide whether to admit to declare the traffic and the performance requirement. We need the QoS routing to find a pair with a bounded bandwidth. We need the router to decide whether to admit the flow. And then once the packet starts to flow, we need to classify into flow queues. Classify packet into flow queues. And then before they join the queue, they need to be policed to make sure they are not overusing the bandwidth. And then once they join the flow queues, they need to be scheduled. The transmitter need a scheduler to decide which queue to serve next, or which packet to transmit next. So putting 6 mechanisms into the control plane and data plane, it's like in the transportation network, you have admission control and QoS routing, deciding which way to go. So first of all, I'm going to speed up a little bit. First of all, the admission control. Okay, so here's an example of admission control that you have a flow coming in with the bandwidth requirement of 3 megabit per second, and the link bandwidth is 10 megabit per second. But we have existing traffic going through this link already, and there's a new flow coming in. New flow coming in with 3 megabit per second. Should I admit the flow? If I take this, the maximum bandwidth, my answer will be no. If I admit this 3 megabit per second, my peak will exceed 10 megabit per second. If I take this, I would say yes, it's quite safe to admit this flow. So either taking this or this is not good. I should take the average. I should take the average. But how do I measure the average bandwidth? I mean, the average traffic bandwidth, the current bandwidth being used. How do I measure the average is an issue that we will see how we measure the average later. And if you want to have QoS, then your queue is definitely not a single 5-volt queue. If it's a single 5-volt queue, then you cannot allocate bandwidth. you cannot allocate bandwidth to specific floors or specific classes. You need something like this with several queues, and then you need to do scheduling here. So the QoS is actually, so among the 6 mechanisms, this QoS is actually enforced by scheduling. QoS is about allocating the bandwidth to different floors or classes, and it's actually enforced by the packet scheduling. Okay, all the others, so this one is the main character, the key role. All the others are trying to support this. All the other 5 are trying to support this. Okay, there's an open source implementation called TC, traffic control. Within it's a kernel module within Linux. It's in the Linux kernel, and it implements the data plane, because the control plane mechanisms, you see the control plane mechanisms are mostly implemented in the user space program. However, the data plane mechanisms about classification, policing, and scheduling, they are implemented in the kernel. So here you will see there's a classifier here. It does packet classification, and then policing, and then scheduling. There's a scheduler here, multiple queue, and it does scheduling here. Within the kernel, it's behind, below IP forwarding. After IP forwarding, you put it into an output queue, and then output device. That's without QoS. But with QoS, you can go this way, then it will go this instead of FIFO. Here it's FIFO, but here it's not. It's multiple queues, multiple FIFO queues. Okay. So it's implemented right after IP forwarding. And it's implemented when with in queue and dequeue. In queue, when you in queue, so what you do is that you the in queue and dequeue have been changed to embed the QoS, the classification, policing, and scheduling. That's in queue and dequeue in the kernel.